In this lecture, we will be completing our implementation of the MIPS microarchitecture. First, a reminder, microarchitecture is the hardware diagram that we've been building up. It's how the computer is actually built, the way that we arrange the registers, memories, ALUs, and connect them with wires. This is as opposed to architecture, which is at a slightly higher level of abstraction. Architecture is what a computer can do and where it can store things. So microarchitecture is our way of implementing a specific architecture. So far, this is the diagram that we've built up. With this diagram, we're able to implement R-type commands, the first things that we added to it. Later, we added this data path, some multiplexers, and some control logic to be able to implement things like add immediate. And then finally, we added branch computation and logic to know whether or not to take the branch to allow us to implement branch commands as well. Since we last looked at this diagram, we've learned about a few new things. One of them is jump commands. Jump commands are another way of changing the program counter. And they're actually fairly straightforward to implement, but we won't be learning about them in this lecture. The other that we've learned is about load word and store word. With load word and store word, we've added a new state element to our diagram, data memory. Load word and store word are the only way that we can access data memory in MIPS. Remember, we can't do adds, subtracts, etc. directly with something in data memory. We have to first read it into the register file before we can work with it. These four elements are called the state elements because they're all that holds the state in a particular program. Put another way, if we know what each of these elements is, then we know exactly where we are in the program and can recreate it on any machine. The program counter tells us which instruction we're operating on or where that instruction lives in memory. Combined with the program counter, the instruction memory allows us to get a particular instruction, like an add immediate command, for example. The register file is where we store our operands, and the data memory is where we store our longer term or larger items. So just like before, when we want to build up a computer, we add in our state elements, and then we add wires between them, and possibly control logic and multiplexers to allow for different commands. In general, the way that we read these diagrams tends to be from left to right. So we fetch the instruction. Knowing where it is, we get it out of instruction memory. We then have to decode it, figure out which wires go where. For example, with an add immediate command, we have a register that we're reading from and an immediate. We need to know where to hook those up to, and we need to know which part of the command they are. Then we read our data, so anything that we need out of the register file. Finally, we execute the instruction in the ALU, which isn't in this diagram yet because it isn't actually a state element. And then finally, we write the result back to the register file or to data memory, depending on the command. As a reminder, store word and load word are I-type commands. I-type commands have this general structure. To start building up the diagram, the first thing that we're going to do is to fetch the instruction. This is the same with all of our commands. To start decoding the instruction, we need to remember, in general, what load word and store word look like. So for example, we might have load word T0, T1, and an offset. So in this case, what this means is load what's in T1, that's our base address, add 8 to it, that combined is the address that we'll be loading from, and put the result in T0. So the first step then is to get that value out of T1. So over here we specify the value for T1, and out of here comes the actual 32-bit value that was stored in the register. Then we need to add that immediate on. To do so, we need to run it through a sign extender because our ALU operates on 32-bit operands, whereas our immediate is only 16 bits. So we need to turn it into a 32-bit via sign extension. Once we have the operands, we run them through the ALU and get the full address of what we're looking for. Finally, we read the memory at that address, bring it back, put that into the WD3, so for write data of the register file, and then this A3 tells us where we're writing to. So A3, in our example from several slides ago, specify T0. After that, we just need to make sure that we move on to the next command. Remember, this is what makes it a computer as opposed to something like a calculator. It automatically proceeds through its pre-programmed set of operations. The 4 here is because each instruction is 32 bits, or 4 bytes, and memory is byte addressable. If we want to advance by a single instruction, we have to advance by 4 bytes. So this computer that we've just built implements a single instruction, load word. We're going to follow the same process that we did before to add the rest of our instructions back to this computer, in addition to store word. So we're going to add things to our data path, and we're going to use multiplexers and control logic to ensure the commands we already have continue to work while the new commands are implemented. Changing a load word to a store word is a fairly straightforward change to the data path. So a store word looks a lot like a load word. We're still reading the address out of T1, adding some immediate to it, 8 in this case. But now we're storing the contents of T0 into memory at that address. So we're also going to need to read what was in T0. So in this case, we have to read T0 and send that into the write data part of data memory. The address computation is exactly the same, and so our address is the same. Also note the changes in the control wires. For a load word, we did not write to memory, so memwrite would have been 0, whereas here it's 1. For a load word, we were writing to the register, so regwrite would have been 1. Store word does not write to a register, it only writes to memory, so regwrite is 0 in this case. The next thing that we'll add is our R-type instructions. The nice thing about R-type instructions is that once we've added one of them, we've essentially added all of them. And as a reminder, this is the general structure for an R-type command. An example of an R-type command would be something like add T0, T1, T2. They're called R-type commands because all 3 of our operands are registers. So what does this command do? We're adding up the contents of T1 and T2 and putting the result into T0. So how does this change our data path? We already had our data path equipped to read from 2 registers. But in this case, rather than sending the immediate to the ALU, we now need to read the second register and send that to the ALU. So we have to add a multiplexer. And in this case, we're going to let through the register value from this multiplexer. If we were to go back to our other commands, this would be a 1 because we'd be letting the immediate value through. So we've completed the first part. We've read T1 and T2, set them to the ALU to be added up. The next thing then is that R-type commands have nothing to do with memory. The only way to access memory in MIPS is through a load word or store word, or load byte, store byte, and so on. So in this case, we simply set memWrite to 0 and then ignore memory. To ignore memory, we need to send the ALU result directly back to the register rather than reading data from memory and sending that back. So we need this other new multiplexer, which for R-type commands is going to have a 0 control, and for a load word would have 1, and for a store word, we would say that we don't care here, because the store word isn't going to write to memory. So for our add command, we're sending the ALU result through. That goes into the write data part. And so the last thing is to know where to write it. From the command, we can see that we want to write it to T0. However, where our destination is stored is different for R-type and I-type commands. So for our R-type command, this T0 is stored in bits 11 through 15, or RD. For our I-type commands, our destination would have been stored in bits 20 to 16, or RT. So in this case, we need yet another MUX to allow us to have our backward compatible change. When we're having an add command, we want to let RD through. And if we were to be doing something like a load word, regdest would be 0, so we would let RT through, and that's the one we would write to. The last thing to add is the branch instruction. Since we have so much of our data path set up already, they're fairly minimal changes. For a branch instruction, we have another I-type instruction, but in this case, rather than having a number, we have a label as our third argument. However, underneath, this label is still stored as a number. If we recall from a previous lecture, this label represents the number of instructions that we want to skip if we take the branch. So for example, we might put a 3 here. So how does this change our data path? Well, we have to do 2 operations at this point. First, we have to check T0 and T1 to see if they're equal. We already have a data path that will allow us to do this. We read T0, read T1, set our MUX to allow T1 through the ALU, and then we subtract them. If we subtract 2 registers and the result is 0, we know that they were in fact equal. This is where the 0 output to the ALU comes into play. Whenever the output of the ALU is 0, this is 1. Whenever the output of the ALU is non-zero, this is 0. So, if the output of the ALU was 0, and we were using a branch command, which we would know from our control logic, then we send a 1 over to this new MUX to tell us that a branch was taken. If either of those was false, meaning this 0 was the number 0 because they weren't equal, or this branch was 0 because it wasn't a branch command, then this MUX will have a 0, telling us not to take the branch, and we can see then that the PC would have proceeded as normal. The last remaining addition then is how to compute the program counter if the branch is taken. In that case, because this 3 is the number of instructions that we wanted to take in this example, we need to convert that to bytes because our memory is byte addressable. So if we have 3 instructions and we have 4 bytes per instruction, then we know that we have to advance 12 bytes. So that's what this shifter is for. So that's telling us to shift twice to the left, which is the same as multiplying by 4, like we did here. So this turns instructions into bytes. We then add that to our current location, and If the branch is taken, that becomes our new program counter. And with that, we have the entire MIPS microarchitecture as far as we're going to learn it in this course.